All right, here we go. We're on Module 12B, Lab 27, the hydrosphere. And the hydrosphere refers to all the water in the Earth, every drop of it. And when you look at the Earth from space, it looks like a big blue marble. All right, let's watch our introductory video.
This is a view of the Earth as it is seen from the surface of the Moon. No wonder astronomers call it the blue planet. Now, if we look a little closer, we'll see where this blue comes from. Here we see a close-up of the Earth with a satellite in the foreground. Underneath, you see an ocean. That, of course, is where Earth gets its blue color.
Oh, that was easy. Quick. All right, here's your first blank to fill in. The hydrosphere, that's the word you're putting in. I'm putting the slide back on. The hydrosphere is the sum total of all water on a planet, whether it's solid, liquid, or gas. We all got that? Yeah?
The hydrosphere is actually the sum total of all of the water that exists on planet Earth. That water is stored in a variety of sources. The vast majority of that water, more than 97%, is stored in the Earth's oceans. Of course, the oceans contain salt water, not fresh water, so the vast majority of the water in Earth's hydrosphere is not even drinkable. Most of the rest of Earth's hydrosphere is fresh water, and therefore it's drinkable, but it's locked away as ice, because slightly more than 2% of Earth's hydrosphere is in the form of glaciers and icebergs. Most of the rest of the fresh water in the hydrosphere, more than 0.5% of the hydrosphere, is also not very accessible because it's underground. This groundwater is usually not visible, but we can see it here because it is being released in a geyser. Less than 1/100% of Earth's hydrosphere is contained in the lakes, rivers, and streams that we normally think about when we think about water. Believe it or not, if we add up all of the moisture that is soaked into the ground, we have almost half as much fresh water as what is contained in the lakes, rivers, and streams of the Earth. The rest of Earth's hydrosphere, about 0.1%, is contained in atmospheric moisture, such as clouds and humidity.
Okay, so here's what's going to happen in the next couple of slides. All right, you have a table in front of you on your notes, yes? So I'm going to give you the first group on the left side there. You're going to write all these down, and then we'll answer the rest of it and the questions beneath those simultaneously. I couldn't figure out any other way to do it, except for putting the whole table up there and y'all just, it's very boring, right? So I want to make it a little more interesting for you. So, in the left portion there, you're going to say the kind of water we have. David has a question, yes?
I don't think we're allowed to write on the table.
Did I ask you to write on the table?
You said there was a table that we're supposed
Oh my goodness gracious. Write in the table in your book, please. All right, so the first blank on the table in your book is oceans. You can write oceans there, and then we'll get to the rest of them as we move.
Oh.
Underneath it, glaciers and icebergs. Then the next one under that, groundwater. These were all mentioned in the video just now.
Yeah, that's what I got.
Surface water, not oceans. Soil moisture, and atmospheric moisture. So those are 6 things in 6 blanks. So this table apparently is in your book, table 12.1. It would probably be a good thing to study for the quiz, which will be next week, I guess. Yes, the quiz over module 12 will be next week. All right, so now we're going to answer the next blank over, the next 2 blanks over, and another question which is below the whole table, okay? Hopefully this will make sense to you as we go. All right, oceans. The type of water found in oceans is salt water. So that's your second blank in the table, salt water. And it is 97.25% of all the water on the planet. That goes in the right column. Okay?
Exact.
Yes, 97.25. That's the vast majority of the water on the earth is non-potable. You know that word potable? That means non-drinkable.
Well, is it possible to make it drinkable?
Good question. We're going to do a little something with that today. That's what our lab is going to be today.
Yes.
It is very difficult to desalinate water, to get the salt out of the water. You can do it. We're going to do it today.
Can you make salt out of salt water? Like you boil or something?
We can, but we have to go through a process to do that. And the
boil
deal
it in
is, the
salt
problem, if I
water.
took ocean water and did the process we're going to do today, which is called distillation, it gets very expensive. So while we can get plain water out of salt water, we can't do it efficiently. We can't do it affordably, you know. So we got to figure out a way. I think we'll talk, at least last time we used to talk about this,
What happens
about
if you
different technologies being developed to turn salt water into fresh water.
What
Yeah.
happens if you drink a lot of salt water? Will it like you get dehydrated?
Yeah, it will make your dehydration worse. Don't drink salt water. Now, I'm not talking about a little salt. I put salt in my water for the mineral content of it. You don't drink ocean water if you're thirsty.
What if I like swallow ocean water and accident?
Yeah, it's all right. A little bit, won't hurt you. Yes.
I know how. Through evaporation.
Right. And so it gets very expensive. My point is, it gets very expensive to do that. It's not an efficient way to
We
do it.
just collect rainwater because it comes from the ocean.
That's true. Right. All right, so here, notice the blank beneath it, beneath the whole table there. It's going to say, most of the Earth's water is salt water in the oceans. Do you see those blanks down there? Okay, am I making sense now about how we're going to fill this in?
Yeah.
I couldn't figure out how to do this without repeating myself a million times. Or just putting the whole table up you there, like I said, would be boring. All right, so let's say, here's our seawater right there. 96.5% of it is water. But this other part right here, this 3.5% is salt, and the salts are shown over here. We have mostly chloride and sodium, so sodium chloride. That's the salt we put on our food, okay? We also have some sulfates. We have some calcium, potassium, magnesium, and what we call minor constituents, whatever those are. All those work together to make all the salts in the water. It turns out that salt water in the ocean actually is very good for you. It's just not good to drink it. But you know what? It's really good. It's good to swim in it. Because we need all these minerals, especially magnesium, calcium, and potassium. We need those, and so it's nice to swim in it. So like I was telling you, with my water that I drink, I have a water filter at my house called an RO water filter, which stands for reverse osmosis. It takes everything out of the water, all the chlorine, all of the fluorine, although we don't put fluorine in the water out here, all the bacteria, anything big. It also takes every bit of the minerals out of the water, all of it. So it's pure water that comes out of there. My husband drinks it and said, this water tastes dead. It's true. So what I do is I add salt back into it, just a little bit, a little tip on the knife right in there, and it's that Himalayan, really fancy salt, right? And it has all these minerals, and I get to I get the minerals back. So it's important to get minerals in your diet, and water is one of the greatest places to get it. Okay, so but also what we're going to find out about salt water is different than non-salt water, than fresh water, more than just the taste of it. All right, turns out it can make you very buoyant. Now this person right here is just sleeping, I guess sitting, reclining on water. Okay, it turns out he's in a place called the Dead Sea, and the Dead Sea is very salty. It's dead because nothing will grow in it because there's so much salt. So it's saltier than the oceans. Yes?
My sister's been there along
Yes.
with my mom.
And she probably went in there, right? She probably
Yeah,
swam
they
in there.
grew up in Israel, so they were kind of close to it.
Nice.
My mother.
I had a friend who went and she said that it felt kind of slimy on her skin. And also, you know how you may have little cuts or whatever on your fingers? And they could tell once they went, they knew exactly where every little cut was because that's all more, you know, that kind of thing. But let's watch a fun little video here about a guy testing
It'd be
salt
terrible
water.
to swallow that water.
It'd be bad.
Hi, I'm Eric Trinidad, and we're here at the Dead Sea in Israel, where we're going to answer the question that we've all been wondering since biblical times. Will a 14-pound bowling ball float in the Dead Sea? Do you think a 14-pound bowling ball will float in the Dead Sea?
I'm gonna say no.
The Dead Sea has attracted visitors for thousands of years, and today it's a popular destination for tourists who come to cover themselves in therapeutic, mineral-rich mud. They also come for the novelty of floating in the water, because there's so much salt in it that many things become unusually buoyant.
Tell me, do you think a 14-pound bowling ball will float in the Dead Sea?
Yeah, I think it's possible. I'm not really sure. I don't know. It could go either way.
About 31% of Dead Sea water is comprised of natural salt.
That's all salt.
This makes the Dead Sea denser than ordinary water by about 17 to 24%, depending on the data you find on the internet. This means that a 14-pound bowling ball could float in the Dead Sea, but not in a tub full of bathwater, or at the beaches of Israel along the Mediterranean, or in a swimming pool outside the old city of Jerusalem.
Down there.
Or even in the Sea of Galilee, where Christians believe Jesus walked on water.
Has anyone ever tried to do this before?
Not as far as I know. Never with a volleyball.
Totally close.
This looks pretty on the top.
So she's just sitting there, like no floating underneath her. That's pretty cool, yeah. All right, so there you go. We're going to see, we're going to have sodium chloride is the majority of the salt that's in there, the main salt that's in there. And the question we have for you, and I believe your book does still pose this question to you, how does a salty ocean support creation science? Do you have a link in your book about that?
No.
No? Okay, if it's not there below the table, then you don't. All right, so evidence for creation, exclamation point. If the earth is as old as the evolutionists say, and as it really the theory demands, it needs to be that old for it to happen that way, then the oceans would be much saltier than they are now due to evaporation and surface runoff. Okay, so where is the salt in the oceans? Where did it come from? The land, right? It came from the land. And so therefore there's still salty places on the earth that can still drain into water sources. Yes.
So one day the Dead Sea is gonna dry up and there's just gonna be big piles of salt.
There's already big piles of salt along the side of it.
Oh, wow.
So yes, the answer. So the thing about the Dead Sea is that it doesn't have an outlet. Water comes into it but never leaves it. And so therefore the only thing it does is evaporate. And there the salt gets saltier. And it takes all the sediments from the ground around it and leaves that salt there. Now, you know, in America we have a salt place, right? A salt sea, a salt lake. It's called the Great Salt Lake. It's in Utah.
Yeah.
And I don't know if you're aware of this, but it's not quite as salty as the Dead Sea. There is actually some life in the Great Salt Lake. It's little krill and things like this. It causes it to be a little smelly. If you've ever been, I've been there, and it was vast. It was huge, but it had kind of a funky smell. And we saw one boat out in there, and so I'm thinking, you know, people don't use it for floating in, I guess. But the real close to it is a place called the Bonneville Salt Flats. And that is some very salty, naturally salty earth. And they're very, very flat. And that's where people drive cars really fast. Do you know what I'm talking about? Cars that's where they set the land speed record because it's very, very flat. And they're driving along a salt flat is what it's called. All right, so if the oceans, the saltiness of the oceans does not support a billion-year-old Earth. It just doesn't support it. It would be saltier. The ocean would be saltier. And so it does kind of support, so it's one of those other things in the arsenal of a creationist to say, well, what about the salty oceans? You know, because when water evaporates out of the oceans, the salt doesn't go with it. We're going to show that in our lab today. All right. Where is the fresh water? Here we go. So your next group is icebergs and glaciers, right back up in your table. It's fresh water. And 2.05% of it is in those glaciers and icebergs. Now, what's the problem with glaciers and icebergs?
They're cold.
They're frozen.
They're frozen, right? So we can't really access that water. Now, technically, if I came across a iceberg and I were thirsty, I could chop a bit off and try to melt it in some way, yes? And then I could drink it. Right, so that would be good. So if you are stuck out in the ocean and very thirsty, don't drink the salt water, but if you see an iceberg, chip it off and try to melt that. But if you're in the ocean stuck, stranded out where their icebergs are, you're going to be really cold and you probably won't last very long. So,
Wouldn't the icebergs have salt in them?
no, the icebergs are freshwater. They came from a glacier.
But if there's an iceberg in the middle of the ocean,
It came from a glacier, which is freshwater.
not even the part underneath the water?
It will be touching salt, but no, it doesn't freeze. It takes a lot to freeze salt water. There is such a thing as frozen salt water. It's called salt ice. It's a little different. It's flat. Have you ever seen the pictures of like a polar bear on a flat piece of ice? That's probably an ice sheet, which is probably salt water. It's very, very cold there.
We learned about that in one of our modules about salt water being less.
Yes, it's more dense, and its freezing point is much lower. Glaciers and icebergs are packed snow that get compressed into sheets of ice in the mountains where it's colder, and then they start to move downward. Now, we talked about this a little last time, right? Didn't we? Did we talk about glaciers last time? No? Let's get that mixed up. Okay, but notice how this is actually a moving river coming downhill. The gravity is pulling it down, but it's frozen. All right, and so we're going to spend a lot of time at this at the end of the module talking about what happens underneath a glacier. It's scraping the earth away as it moves down. All right, so when it gets to the end right here, though, you see we're at a water source right here. It gets to the bottom of the mountain. These things will fall off. Gravity will pull those off. So this is called calving. I mentioned that. I thought I mentioned to y'all last week about calving. Like a cow giving birth to a baby. That's the word for it, calving. Calving is when large chunks of ice break off of a glacier and fall into the water, creating icebergs. That's where the icebergs come from. All right, all icebergs come from glaciers. All right, so therefore they're up in frozen areas to the north. So we're going to watch a bit of calving here. People go on tours just to watch this.
Glaciers and icebergs contain a little more than 2% of the water in the Earth's hydrosphere. This is the Mendenhall Glacier in Alaska. As you can see from the video, a glacier looks a lot like a river of ice flowing down a mountain. In fact, that's what it is. A glacier is a massive collection of ice whose weight is forcing it to flow down a mountain until it encounters water, where it then floats. Eventually, stresses in the ice cause large chunks of the glacier to break off in a process called calving. The broken pieces then float in the ocean as icebergs.
Okay, here we're going to see people on a tour to go watch calving in process. And they pay money to go on these tours.
Look at it.
Okay, so the only thing you have to do is, in that situation, you have to be careful because sometimes a large enough chunk will come off, creating a giant wave that will swamp your boat. And that's happened. That happened very recently, and the people all were dumped over in their boat.
Really cool.
I can't remember. I'm super optimist. Let's say no. They were fun. Okay, the next group, we're talking about groundwater. The largest source of liquid water is groundwater. It's fresh water, and it's 0.685%. So that's going on your chart at the top. And I don't have anything underlined, do I, besides those things? Okay, so the largest source of liquid water is groundwater. Notice it's under here. Have you ever, anybody here have a well at your house? You have a well?
I used to.
A well? Okay. So you had to dig down, and when you dig down, you hit water. So what kind of water do you hit? You hit groundwater, and that groundwater is fresh. And we use that. So we take that. Now, I don't know about y'all. I use a service called Aqua Water. That's my. Y'all know the name of your water service? And have you seen the big water towers, right, with the smiley face on there? That's Aqua Water. It's just a company. It's a private company that goes and collects water, puts them up in those big towers, and you know why they're up there. So the gravity will pull it down and come to my house and give me some water pressure. Okay, but they got to get it up there. They got to put it up. They got to pump it up there first, and then it sits up there.
That's how we get water pressure.
That's how we get water pressure, just the water behind it. Yes, you'll lose water pressure if the thing was empty or something it leaked out and you still had water in the lines, you wouldn't have any pressure because there's nothing behind it to create that pressure. So they have to go get that water from somewhere, and what they get it is they get groundwater from something called an aquifer. And the aquifer runs underneath us. And in the Bastrop area is the beginning of what is known as the Edwards Aquifer. And it goes out to the west and south, and I know that the city of San Antonio really wants our water because they have a lot of people in San Antonio, and there have been some legal fights between the people in our area and the people of San Antonio because we said, no, we don't want to give you our water because water is a precious resource, right? And during times of drought, the groundwater will get lower, right? And we'll start to lose water, and so we don't want to have that happen. So you may want to think about places to get water, like a well of your own, or have you ever heard of water catchment? Water catchment, off your roof in the rain, when it rains. You can have it come into a little spout down into what is known as a rain barrel. Anybody have a rain barrel?
We have a rain tank. We don't use it anymore.
What'd you call it?
It's like a tank.
A tank?
It's a really big tank. And
Oh, nice. You don't use it anymore?
No, because we have a water heater now.
Yeah, so you got a water company or whatever. But if you needed to use it in the future, you could, right? By catching water. Yeah, that's a good thing to have. All right, so groundwater, here it goes. After glaciers and icebergs, the largest source of fresh water is the groundwater flowing underground. That should be a blank underneath, yes? Am I correct? Okay. All right, so that is saying the same thing we were just talking about up on the table. The table was just giving us the statistics, right? So here we say we're putting that in our blank. And we see right here a house that has put a well in by reaching down here and finding the groundwater. That was a pretty deep well. Look, this was a shorter well here to water their garden. That's a really great idea, so you don't have to have the hose from your house or whatever, okay? The only problem you have to worry about with this groundwater is that it hasn't been treated. In other words, it might have stuff in it, namely mud, you know, so as long as you have filters and stuff like that, it'd be okay. But it hasn't been treated for any kind of waste that might end up there. The water coming from the water company, they have to treat the water. And one of the ways they treat the water to make sure there's no microorganisms in it is to put chlorine in it. And that's why you smell the chlorine. Just like a pool needs chlorine. You know why we put chlorine in a pool? To keep bugs from growing in it. And when I say bugs, I mean microorganisms and algae and things like that. All right. Surface water, not oceans. Surface water is found in lakes, rivers, and streams. It's mostly fresh water. So that's what you're going to put in that second blank under surface water, not oceans. You're going to put in mostly fresh water, and it's 0.009%. This is the water we drink. Well, the groundwater. We drink the groundwater too. But this stuff coming from lakes and rivers and streams. And you know, I said mostly fresh water because think about the Dead Sea and the Great Salt Lake, you know. And I suspect there's probably other salty
Salt rivers.
Lakes elsewhere. Not really rivers, but because mostly the Great Salt Lake is the same. It's the endings, but it has no outward. Just like the Dead Sea, it has no outflow. And that's why the salt all concentrates there. And I also tell you the Dead Sea is what we think is the lowest place on the surface of the earth that's not under the ocean, right? So they call it the navel of the world. It's the lowest place. That's at the Dead Sea. Some people think the Garden of Eden was there. Don't know. All right. This is back up on the table again. The soil moisture is the water held in soil is fresh water, and it's 0.005%. And we don't have a corresponding blank below for that one. All right, we can't get this water very easily because it's in our soil. It's soaked up in, it's maybe muddy at this point, you know, so if we wanted to get that, if we're trying to drink the water out of the soil, it's tough to get it from there. And then we have our atmospheric moisture. It's fresh water. It's 0.001%. And presumably, if you added all those percentages together, we should end up with 100. I didn't do that math, but I suppose it would be that way. All right, so now your table should be completely filled in. Is that correct?
No,
Yes.
What are you missing, John?
I'm missing something. I'm not too sure.
Well, I went through everything. Oh yeah, you're supposed to put the percentages in here. So you're supposed to say salt, fresh, mostly fresh, fresh, and then the percentages. You just put the percentages in the middle grouping there. As long as you have what the percentages are, then you're good.
So just switch them.
Or just put your percentages over here to the right. Okay, so now we're going to look at the hydrologic cycle. It's the process by which water is continually exchanged, these are blanks, exchanged between various water sources. So that's the last sentence underneath that first table, yes? And now we're going to come to another table, right? All right, this is called the hydrologic cycle. That's a fancy word to say the water cycle, right? The water cycle. Y'all all know the water cycle, correct?
Yes.
Okay, so here's our water cycle. It's going to go Every bit of water has been recycled, yes? The water we drink today is the same water that Jesus drank back in the day, yeah? It's all the same water. Right. There's nothing new coming from anywhere. It's self-contained inside the earth. The atmosphere is holding everything in. So we call it the water recycling process. And in the next chart, what you're going to do is write down the shuns. T-I-O-N-S, the shuns. All right, so let's see where we're starting. Transpiration. Transpiration. So transpiration is water that evaporates out of plants. It actually comes out from the underside of the leaves of plants. It drops of water on you. That's why standing under the shade of a tree in the summertime is much cooler than standing under the shade of a barn. Have we talked about that? No. Okay. Evaporation, the process by which liquid turns into a gas. I believe all you're writing in your chart is just these words, right? You don't have to write all the data about it. But everybody knows what evaporation is, right? Next, we have condensation, the process by which a gas turns into a liquid. Like the side of your lemonade glass out on a summer afternoon, right? It's all wet on the outside. That's coming from the air. It's not coming from inside the glass. Otherwise, you have a really, really crummy glass. Precipitation. Water falling from the atmosphere as either rain, snow, sleet, or hail. Freezing rain's another one. Anything falling from the sky that's made up of water, even if the water's frozen. Distillation. Evaporation and condensation of a mixture to separate the individual components. We're going to see that. That's what our lab is going to be today, a distillation lab. Mostly we use distillation in a fixed environment, but it can happen naturally on the earth in certain situations. Percolation is the last one, the process by which water moves down in the soil toward the water table. So that water that's underground, right? It gets there by the rain soaking in through the soil, and gravity keeps pulling it down. And as it goes through the soil, then it goes through the rocks, and it goes through all that stuff. It actually is a really great filter for the water, so the water gets filtered.
What do you mean by water table?
The water table is how high the water is. Like how far do I have to dig to get my well in? Some people can dig 10 feet and there's the water. Some people have to dig 300 feet because the water table's lower. At my house, the water table's very high, except it's a big slick of mud. And because of that, it sort of sits on the mud, and then it's not a real good source of water because I get just muddy water. So I have to dig deeper past that first water table down to the bedrock. So that's why we don't have a well at my house. All right, do we have all the shuns written down? Put a star by this little chart. You're going to probably want to remember that for next week. Even knowing that. Okay, so here we have our transpiration from the plants, evaporation from the lakes and streams, condensation into the clouds, precipitation, surface runoff, that would be our percolation right there into our groundwater. Okay, we'll go back through here. All right, let's watch a little something on this.
You may think every drop of rain falling from the sky or each glass of water you drink is brand new, but it has always been here and is a part of the water cycle. At its most basic, the water cycle is how water continuously moves from the ground to the atmosphere and back again. As it moves through this cycle, it changes forms. Water is the only substance that naturally exists in 3 states on Earth: solid, liquid, and gas. Over 96% of total global water is in the ocean, so let's start there. Energy from the sun causes water on the surface to evaporate into water vapor, a gas. This invisible vapor rises into the atmosphere where the air is colder and condenses into clouds. Air currents move these clouds all around the Earth. Water drops form in clouds, and the drops then return to the ocean or land as precipitation. Let's say this time it's snow. The snow will fall to the ground and eventually melts back into a liquid and runs off into a lake or river, which flows back into the ocean, where it starts the process again. That's just one path water can take through the water cycle. Instead of snow melting and running off into a river, it can become a part of a glacier and stay there for a long, long time. Or rain can seep into the ground and become groundwater, where it's taken up by plants. It can then transpirate to gas directly through the leaves and return to the atmosphere. Or instead of being taken up by the plant, the groundwater can work its way up to a lake, river, spring, or even the ocean. As you can see, the water cycle can be a very complicated process, and all its paths through Earth's ecosystems are complex and not completely understood. Water is essential to life on Earth, and fresh water is a limited resource for a growing world population. Changes in the water cycle can impact everyone through the economy, energy production and use, health, recreation, transportation, agriculture, and drinking water. And that's why understanding of the water cycle has become one of NOAA's grand science challenges. NOAA studies all aspects of the water cycle: ocean, weather, precipitation, climate, ecosystems, and our impacts on it.
All right, so it said at one point that it was a limited resource. Well, not really. It's kind of unlimited, right? We got all sorts of water out there.
Just run out.
Yeah. So a little more about distillation now. Here's our blanks on distillation. Distillation is the evaporation and condensation, there's your blank, of a mixture to separate out the mixture's individual components. The hydrologic cycle clears the water as it moves through various sources. So where this distillation can take place is actually in the earth as it moves down there. It acts like a filter. Okay, so you can see right here, this is, if we had a second lab to do, so in other words, if I broke this into 2 labs, we could have this lab to do. So I feel like it could support 2 weeks work on this deal. So we would take a bottle like this and we would have in there some cloth covering the end of the bottle here. We have the bottle upside down. Fine sand, charcoal, coarse sand, rocks. We would put muddy water in the top and let it come through all those little portions and to see how it filters out into fresh water. And then we would drink the water. Maybe. It does, yeah, it really does work. So now, if it were salt water, however, the salt would still be in the water. Salt's too small. So we can't use this type of deal for this type of filter situation for water. We can do a bigger distillation process, which takes the water and instead of just using gravity to come through there and just causing that filtration, we could boil it if we boil the water. But we have to recondense it, and that's where the problem comes in. All right, so residence time is something apparently it's not in your book anymore, or at least it's not in your lab book anymore. It talks about how long the average time a particle will stay in what system it's in. So what system do you think, as far as the ocean, the stream, the glacier, will a drop of water be in there the longest?
Glacier.
Maybe a glacier, maybe, yeah, we'll see. What about the shortest time it will be there? Ocean?
Lake.
Lake, so fresh water. So here we have this used to be in chapter 5. So I don't think you have this anymore, I don't know. But look, residence time, ocean, 4,000 years. So a drop of water in the ocean can last, and that's simply because it's so massive, right? It could be down at the bottom, up at the top, it's not gonna evaporate till it's at the top. Glaciers and iceberg, that's next. So if that had been freshwater source, and y'all would have got it with the glaciers and iceberg, 1,000 years. Groundwater, 2 weeks. Up to 1,000 years, depending on how deep in the earth it is. Soil moisture, pretty short. Look, atmosphere, 10 days. That makes sense, right? It's going to rain somewhere. Lakes, 10 years. Rivers, 2 weeks. Swamps, 1 to 10 years. Interesting. Okay, because swamps are very still. Not a lot of motion. Not as much evaporation if there's not a lot of motion. All right, so that's something that would have been in the old deal. All right, so now we're moving on to something called weathering, which is a whole different thing. Which could have been another lab. Yes.
So how can it stay in there for 4,000 years if a water droplet comes, stays on the top, and then gets evaporated the next sunny day?
Right. So this is what we would call an average of the water. So because we have to consider the water at the bottom, we'd average those out.
So that's like the longest can be.
Yeah, I guess it could be longer if we're averaging it, right? Okay, so now we're moving on to now we're looking at what does the water of the earth do to the earth. It weathers it. It changes it. All right, so we're going to see one of the physical forces of change on the earth is called weathering. Weathering. Weathering is any process that breaks down rocks and creates sediments. Is this on your second page now? Okay.
Mechanical.
Okay, we're gonna get to that. Yeah. We've got these blanks written in. Weathering process and sediments. Two forms of weathering include, John Mark just said it, mechanical weathering and chemical weathering. All right, it's just like they're described. Mechanical means there's something moving past it, scraping it off, something like that. Chemical means there's chemical change taking place. So now we're going to look at each one of these. Do we have another chart? I found this to be very annoying to do this way. All right. So we're going to start with mechanical weathering, and here's, I numbered them. You're going to have 1, 2, 3, 4 things to put in. So the first type of mechanical weathering, there's 2 of them we're looking at, ice wedging and frost wedging. So that ice wedging goes in one box, frost wedging goes in the second box. All right, they're very similar, however. Okay, ice wedging means that ice has frozen inside a crevice of a rock, and when it froze, it expanded, because that's what water does, it expands. And then when it melted away, leaving a crevice in the rock. Okay, but frost heaving is very similar. It's just it's smaller pieces. So little tiny cracks would have the frost in there, and they might form off some sediments from that. But we're going to end up with our ice wedging that's going to create things like this. So giant rocks can be broken up by just simply ice freezing and thawing in there. So it's quite powerful. Water's a very powerful force on the earth. All right, abrasion is in box number 3, abrasion. We have water abrasion and wind abrasion. You can see here some rocks that are very smooth. Has anybody ever taken rocks and put them into a rock tumbler? What do we call that? A rock, what is that called?
Tumbler.
It's just called a rock tumbler?
Yeah.
Okay. And you have sand in there with it, right? And it's very loud. It's put out in the garage because it's too loud to be in the house. You know, turning all this around. And what does it do to your rocks?
It makes it smooth.
Makes them all smooth, right? And it does that through abrasion. Abrasion means rubbing. All right, it's like sandpaper. And then we put sand in there to do that. And so we can see that rocks can be smoothed out and turned into these beautiful pebbles. If you find a rock naturally that's smooth, what can you tell me about that rock?
Probably been by water.
It's probably been in a brook or something, and when I say a brook, a river or something where water was running past it. Okay? And the water and the sand abrased it and caused it to be smoothed down into a pebble. We usually call that pebble. Well, wind can do it too. Wind can cause abrasion, and we've seen those like the hoodoos and things like this, these formations in deserts and things. Deserts have a lot of sand that's being blown around, and we have this interesting little...
So it's sand abrasion.
Right, but it's the wind doing it, and the water doing it, both using sand mostly. Now I wanted to show you this picture. Let me turn the light so you can see it better. This is called Longhorn Caverns. Has anybody been?
No.
It's just in Kingsland, just up the road, about 2 hours away, maybe. But if you're going to Marble Falls, it's close enough to Marble Falls to visit it. And when I was, my brother-in-law has a lake house up in Marble Falls, and we were there, and we had my daughter-in-law visiting. I was trying to impress her to show her how awesome Texas is, because she's from Arkansas, and she's married to my son, and I want her to come live in Texas, so my son will be close, right? They now live in Tennessee, but they'll hopefully come back. But I wanted to show her this, so I said, let's go show her something really cool. So we went to the Longhorn Caverns, and I thought I'd been there as a kid or whatever. Yeah, I had never been there before, and they taught me something I didn't know. It's an abrasion cave. So in other words, what came through it wasn't about the dripping of the slow stuff with the stalactites and stalagmites and stuff like that, right? It was like water rushing through with a bunch of rocks and sand in it, and it carved out this beautiful interior. Now it was still full of this stuff. It still had the rocks and the gravel and the sand and stuff still in it. And during the 1930s Franklin D. Roosevelt program, the CCC, remember we talked about the CCC, the civilian, what's it called? The Civilian Corps, whatever the other C is for.
Cave.
And these guys, we talked about how I'm pointing to people who are in my history class. We talked about how guys came and built that place in Bastrop State Park. Well, they also worked at this state park, and they cleared all the stuff, all the sand and the rocks and stuff out of the Longhorn Cavern, leaving these beautiful walls here. And so, of course, they put electricity and lights in there. If you turn the lights off, it's pitch black. You can't see anything. You're in the ground, right? But it's this beautiful, beautiful cave. So if you ever get a chance, If you're near Marble Falls, tell your folks, hey, here's a really cool cavern close by. All right.
The water doesn't come back through there.
During flooding times, it actually does.
It
Yeah.
does.
So they close it during flooding times, but it doesn't flood very much out that way. All right, number 4 in your blanks, biomechanical. Biomechanical. So what's happening? Bio part of it's the tree. Mechanical is the tree grows literally through rocks. Have you ever seen a sidewalk where the roots of a tree are pushing the sidewalk up? Sidewalk's pretty hard, right? But the tree roots are more powerful. So this shows you the tree growing right through a rock right there. I'm cracking the rock, and when it cracks it, of course, it's going to change the rock. There's going to be little pieces of sediment on the rock that fall off. And when we have sediment, that's going to join into the soil. We're going to make new soil, that kind of thing.
And new rocks.
And new rocks. All right, now 2 types of chemical weathering. So in your box here, you have 2 boxes there. You're going to write in one box hydrolysis. It has to do with water coming in. So the rocks, when they sit in water for extended periods of time, they begin to break down because the water, typically the water that comes from the rain, has a little bit of acidity to it because of the CO2 that's in the air. CO2 is acidic. So we'll have some chemical breakdown here of that. And then oxidation is exposure to oxygen, to air, and rocks that have any kind of metals in them. Those metals will oxidize, namely iron will turn red. So red rock, close by, it's red because it's called red rock because the rocks are red. And the rocks are red because they've been exposed to oxygen, and the oxygen has made the iron oxidize and turn reddish color.
Is it only iron that does it?
Called rusting it. Some other things do too. Some other metals do as well, but iron's the famous one, and because it turns that red color. But there are other things. Copper oxidizes; it turns kind of green. Verdigris is what they call it. All right, so those are the 2 types of chemical weathering. Okay, erosion specifically has to do with the process that moves sediments. So sediments are created. We have the weathering causing the breakdown of rocks. And then we have erosion will carry those rocks away to somewhere else. So it's really important you understand that erosion is it's carried away. All right, so I've taken that sediment and moved it to a new place. Did y'all put that in a blank, moves? Everybody got on that? Okay. All right. Features created by water include. Now you have another chart, and it's got 5 boxes in it. I'm going to approach them one at a time. Okay, number 1, V-shaped valleys. V-shaped valleys. So we have a river that cuts in to the ground, maybe just a big heavy rain or something, and then as it works in it, it erodes away sides here until we have like this valley with the river coming through it, and it's got a V shape to it. So if you have art class and you draw your valleys and your mountains and this kind of thing, and there's one, look how gorgeous that is, right? That's definitely V-shaped, huh?
I wonder why it only makes V's.
Well, there's other shaped valleys. But in this particular one with the water coming from a river, it makes a V shape. Yes?
So, what is a canyon a V-shaped valley that just hasn't gotten eroded enough to be
I would go the opposite way. I'd say it's a V-shaped valley that got eroded more.
So it's not
Opened
a
it
V.
more. It's not a V anymore. It's flat on the bottom. Yeah. So a canyon is a little different, but it may have started as a V-shaped valley. But we have plenty of V-shaped valleys left. Okay, waterfalls. You think about waterfalls. So a river's coming. So to have a waterfall, of course, I need to have a higher level and a lower level. Yeah, that makes sense, right? Because it's got to fall somewhere because it's water that's falling. So how does that happen? We can have that happen suddenly with an earthquake can cause the land to shift like that and make a brand new waterfall. That can really happen. But mostly what we have is we have just a downhill kind of a slope, and the river's coming and going down the hill like this and collecting in a little, pond beneath there because it's flowing downhill. Well, what'll happen is some erosion will start to take place on that face of the rock, and we have something called a plunge pool forming right here. And it kind of deepens the area because the water kind of falls with a little more violence now. And when it does that, it carves out a little area. The water just erodes the dirt underneath it. And then look what happens. That face of the rock falls off and gets carried away, and it causes this to be very steep, and then the water, instead of flowing down a hill, it's plunging over a cliff. All right, so it's the water that forms the cliff in the first place, but now it's going to plunge past it. So I'm going to give you this picture. Everybody know what this is?
Niagara Falls.
Niagara Falls. Niagara Falls. This is the side, this is the Niagara River that's coming down here. There's also, it splits off right here. Excuse me, this is Goat Island. And on this side right here, it's, so the Niagara River forks off like this. We have another waterfall on this side, but that's in America. That's in New York, a place called Niagara, New York, near Buffalo, New York. But this side is Canada. So if you want to see it's the bigger fall. It's got the more water coming to it. It's called the Horseshoe Falls. That's in Canada.
So people from Canada and America can see it without crossing the border.
Yep. So I was in Canada and looking at it here, and I just looked to the left, and there's New York. But I could just, and there's a bridge called the Rainbow Bridge. You can walk over and just go into New York. But I think Canada's have a little problem with Americans coming to Canada these days.
A little border patrol.
Yeah, they don't want us coming over there. All right, but notice this. Look how that is eroding kind of at a pretty fast pace. So really what happened at the beginning, it was right here. So let me show you this, it'll help a little bit. At the beginning, see how it was right across there. We're looking at it from the other side now. And in 1764, it was eroded to here. 1819 to there, 1842, 1886, 2011, it's now eroded to about where it is now. That water's going over there very violently, and therefore it's going to erode that away. And so that's going to just become a deeper and deeper horseshoe. And that land, what's happening to that land that's eroding away? It's being carried down the river, farther down this way. And there's a lot of debris down at the bottom, yes.
Didn't one person fall down in a barrel?
Several people have tried to go over the falls in a barrel, kind of in the barrel to survive it. And there's been at least one survivor that went over, but there's been lots of people who did not survive. I wouldn't recommend it, yes.
Has anyone survived going without a barrel?
No. It's very far. I wish I could tell you how many feet that is down to the bottom. I've been on a boat the boat came right around here. And so you get completely wet when you have to wear a little poncho, and they put it on you, and it's called the Maid of the Mist or something like that.
Will it just keep eroding?
It'll just keep eroding as long as the river flows. Here's an interesting deal. There was a time when there was, this is Canada, way up the river. It froze up there, and it caused like an ice jam in the river and stopped the flow of the water. So there was one time in the history that anybody knows about that there was no water flowing over Niagara Falls because it had been dammed farther up by ice. It wasn't frozen. It's kind of hard. The water, it's fresh water, so it could freeze, but the problem, all that motion, it tends to not freeze. And so we have never had it frozen coming. A waterfall can freeze, but not one this big. It doesn't usually do that. But they have pictures of people walking around on the rocks at the top of the falls with no water going over.
Yeah, so a bunch of scientists took it as a time to, look around.
Yes.
Explore, right?
It was in 18 something. Yeah, we have photographs of it.
They found gold.
They found gold?
Like a box.
Oh, a box of gold. Somebody had dropped it.
Yes.
I wonder what they did with that gold.
Museum.
Finders keepers, finders keepers. All right, number 3, floodplains. So we have a river coming through that. We kind of understand this because we live in a city with a river coming through it. The Colorado River flows through Bastrop, yes? You ever seen it when it overflows its banks?
Yes.
You ever seen Fisherman's Park when it's overflowed? It's completely over the top of Fisherman's Park. I mean, you can see the little rooftops of the play area above the water. That's it.
And we have a fence on the floodplain of it.
Okay, so you're talking about the floodplain. So if people build their houses in the floodplain, sometimes banks will not give them the money to do that. Why is that? Well, their house could flood, and it could ruin the house. And the bank's like, well, what are we gonna do if you can't pay your mortgage or whatever? Otherwise, what they'll do is they'll make they require those people to purchase flood insurance, and flood insurance is through the government, and it's pretty cheap, I guess.
Don't live in the floodplain.
Don't live in the floodplain. Yeah, but they'll call it like the 100-year floodplain, and then you have to, what's the next question? Well, when was the last time it flooded? Was it more than 100 years ago? Because that means it's due for a flood, right? So if you say it flooded 10 years ago, I'm safe for next 90 years, right? Something like that. It's not exact, obviously. All right, number 4 is called meanders. I love meanders. This is how the rivers will flow, and as they move downstream, certain things will cause them to, move out of the way. Like if there's a big boulder or something, it'll move. Gravity will even do that. And they will find the path of least resistance. And they will flow on that path of least resistance. Question?
Never mind.
Okay, so we call that a meandering river. And this is a really good example of one right here. Don't know where that is, but it's beautiful.
The Amazon is like that.
The Amazon? Okay. But it's maybe, really, because
The Amazon.
I would say it's got so much growth that it's kind of hard to see the river itself, the Amazon River, right? Because of all the jungle that's around it.
So
Okay.
instead of going straight from there to there, it
Right,
goes
right.
loop.
Have you ever, so the Colorado River meanders, and meanders all over the place. In fact, if you've ever driven anywhere, you're like driving, you go, what are we crossing now? Oh, the Colorado. Okay, next, well, what are we crossing the Colorado? Well, what are we going to the Colorado? We just keep crossing the Colorado River, you know, because it meanders so much.
Which
So-
one? Which Colorado?
The Texas one,
Oh, okay.
not the Arizona one. All right.
We crossed this one like 10 times going from here.
Right, if we were just, yeah, we were still crossing that same river. Okay, sometimes a meander will operate in such a way because of certain changes, maybe some weather events, rains, things like this, and they will cut off an end of it right here. It'll get cut off, and like this will connect to here and leave that cut off, forming what is known as an oxbow lake. So that's an oxbow lake right there. It used to be just a meander, and over time maybe it just got filled in with some sediment or something like that. Maybe just the flow didn't go past here very much anymore, and we end up with an oxbow lake. Typically if you see an oxbow lake from the sky, it's kind of muddy looking because it doesn't really have any flow anymore to it. So therefore it doesn't have kind of fresh flowing water. It's got more of a little swampy kind of situation going on there. But that's called an oxbow. So technically these are all called oxbows. All right, so an oxbow of course is the thing you put on an ox's neck to drag your plow or whatever through the land. All right, features formed by sediment deposition. This is a new set of blanks, yes? Features formed by sediment deposition. We have two things. Number one, alluvial fans. So your first blank says alluvial fans. And what we have essentially is water running down from a height and then spreading all of its debris, all of its sediments into a fan type of a shape at the bottom of the hill when they get to the bottom of it. And it kind of forms a fan. All right, here is bad water in Death Valley. You can see that alluvial fan, beautiful, right here. Now Death Valley, it's all sediment, but it got there somehow. That means there was a time when water was flowing in Death Valley. But do you want to go to Death Valley today? No. Guess what happens to Death Valley? Death. You die. Yeah. There's no water. It's a bad desert. And if you're stuck in the middle of Death Valley, yeah, you did. So, unless you brought a lot of water, I guess. I'm guessing there are people who will hike through there. I don't know why. All right, the next one's called the River Delta. That's the next blank over. River Delta is it's similar to alluvial fan, except it's ending at a water source. So it's water coming downhill from gravity, and it's ending in a water source, and it forms this sort of fan shape here, or a triangle, and a triangle in the Greek letter is called delta. And so we call these a river delta. Who can tell me what river we're looking at here?
Nile.
That's the Nile River, yes. And it's flowing upward to the Mediterranean Sea. You can see some sediment being dropped off right there. This, by the way, is called the Fayum. That's an oasis. And it's the water coming off of the river in a little tiny thing, but this is growing right there. All the green stuff is stuff that grows because Egypt is a desert. But they had this incredible empire there for thousands and thousands of years because of the Nile River, giving them that fertile soil. Yes?
So, people say that, what's it called? The world environment change, I forgot what it was called.
Global warming?
Yeah, that. Global warming. They're saying that it's just happening now, but in the Egyptian times, they would measure the height of the lake so that they knew what times they needed to do sacrifices and all that.
When you say the lake, you mean the river?
So-called gods.
Yeah, the river, the Nile River.
But it would go down sometimes, it would go up, so.
And they had a flood every year, but there was never any rain.
Yeah.
So that's kind of weird to have a flood with no rain, right? Because the rain happened way down here somewhere in another country. They had to find that. It took a long time to find the source of the Nile. All right, so your point being is that it's the same as it's always been. I agree. I agree with you. Features formed by groundwater erosion. So, in your first blank, you're going to write stalactites. And we remember that by hold on tight, right? They're hanging from the ceiling. There you can see them right here. All right, and then second one is stalagmites. They push up with all their might. I put it here thinking those were stalagmites, but that might be a reflection. You think that's a reflection?
It is.
There's a reflection here for
Some
sure.
of them are reflections, some of them aren't.
Okay,
As I
so,
see
but,
it.
and here the stalactite and the stalagmite met to form a column. Yeah, so that's a really cool, you know, if you ever get a chance to go to see, this is a normal cavern. Like Longhorn Cavern, Longhorn Cavern's the abrasion cavern. The one in Georgetown, what's that called? Inner Space Cavern is formed this way. Where over time, you know, it was hollowed out, but then it left these little drips and things like that, yes.
There's different ways of remembering it, and I always know stalactites because there's a T in it, it's for top.
T for top, okay, good. And how do you do?
I just know it's not the top. Because
It's not the top.
T is the top.
Dave, do you have a question?
No.
Okay. All right, the other thing and the third thing over there is a sinkhole. A sinkhole.
I love sequels.
Oh, sinkholes are terrible. Sinkholes will catch you off guard and they'll swallow your car right there. You'll swallow your house. Swallow all sorts of stuff. It has to do with water hollowing out the space underneath whatever just got sunk. Right? It hollows it out, leaving it not being held onto very securely, and everything falls in. Look at that. There's a car there that's underground. I mean, underwater right there. There's a second. Okay. All right. Features formed by glaciers. Now we have another chart, y'all. 1, 2, 3, 4, 5, 6 things we're going to put here. Whew. The first one's a U-shaped valley. Okay, we know that the river caused a V-shaped valley, coming through there kind of quickly like that. The U-shaped valley is formed because the glacier is moving much more slowly than a river, yes? And it's coming through and causing that U-shape. The next thing is called a cirque, C-I-R-Q-U-E. It means circle in French. Okay, and what happens is as the glacier is moving down, sometimes it'll carve out something that ends up looking like a bowl, like a circular bowl. And then when it melts, the lake that forms in that little bowl is called a tarn. But the tarn is not on your chart, so we're not putting tarn on there. But the cirque gives rise to the tarn. You can see the cirque is here, and the tarn is the lake that forms at the bottom of the cirque. All right, next is ridges or horns. Ridges/horns. So we can see these ridges, also known as an arête or an arete. Here's our cirque over there, making that circular thing. And then some horns that are formed, and probably one of the most famous horns in the world will be the Matterhorn, right? The Matterhorn. And you can see it's very spiky, and that's because glaciers formed that. Okay, next is glacial lake. Glacial lake. And the glacial lake forms on a flat area like this. So as the glacier is coming down, it's kind of not a very steep slope. It's a much more shallow slope. It's coming down, and then it's scraping away, leaving this area. And then we're going to see this ice on the top will eventually thaw, leaving a lake behind it called the glacier lake. This right here is saying that there's 2 mechanisms by which this happens, but I'm looking at it and I can't find a whole lot of difference. Water rising and then melting here, I don't see much of a difference. But basically what's happening is we're having a glacial lake form on a flatter surface. Because then we have something called a kettle lake. A kettle lake or a kettle moraine can form as well. And how that happens is as the ice is pushing off the glacier and coming down a hill, sometimes it'll bury a chunk of the ice in the ground, and the glacier will keep on moving. It'll move past, leaving this, causing that to thaw later. So it hollows out a little spot right here. So here's some buried ice chunk. Over time, we have that little lake right there. So it's a little, not a nice flat lake like a glacial lake, but these little round lakes, kettle lakes.
Deep.
Like a kettle that you cook in. Kind of deep, depending, yeah. All right, so depressions form underneath the glacier remain after the glacier's melted. All right, next is glacial erratics. The word is erratics, E-R-R-A-T-I-C-S. And what's happening, my glacier's moving up through here. It's very powerful, it's heavy, water's heavy even in its ice form, and as it's pushing past, it'll break off some rocks. Okay, and when the rock gets broken off, it actually gets transported as the glacier moves. And if it's on the bottom, it'll actually abrase the surface underneath it, causing a U-shaped valley. It's pretty cool. It just kind of scrapes it along. With my Science 4 kids, I had a frozen water balloon with dirt and rocks on the bottom of it, and we held it and we scraped it against some clay, and so it showed how it scraped it away. It made my hand very cold. It's very cold. I made Ollie hold it. Where's my helper in that class? Okay, so then as the glacier retreats or the glacier melts, it leaves it sitting there. It leaves the rock sitting there. So in some places you can find things like this, giant boulders laying there. People say, how did these get here? Oh, a glacier dropped them there. Okay, I know there was one at some university somewhere and they wanted to move it, and just getting able to move it, they had to cover it with chains and these big machines and stuff like that to move them. Look at that one, isn't that awesome? That's an erratic. Looks like it's fixing to tumble at any time. Okay, I think we're gonna probably skip our, there was a cool video about glaciers, but we don't have enough time.
We do next week?
No, because we're moving on to a whole new deal. Okay, so here we see our U-shaped valley coming through here. Notice here on the edge, what happens here on the edge, we have something called a hanging valley. Here's a U-shaped valley meeting a U-shaped valley, and what does it result in? Waterfall. Waterfall. Pretty cool. Okay, but notice we have our arete, which we called something else. We called a ridge, I think. Our horn right here. We have a tarn, a cirque, and all those different things right there. So if we had more time to spend on that, it'd be cool. All right, features formed by wind. We have sand dunes. And we have something called a loess. A loess. This was new for me. A loess is sediment formed from wind-blown dust, a plastic, predominantly silt-sized sediment that is formed by accumulation of wind-blown dust. Now, I'm going to go ahead and play a video about a loess. Oh, here in America, our loesses are found in the Great Plains here. We can see, and so what's kind of interesting is that it does have fertile soil, but as things blow away, it takes the fertility away, and we have a problem. So a loess is typically a bad thing. So the video I'm going to play for you is talking about how to revitalize a loess so that it doesn't stay that. While it's playing, I'm going to be getting your lab set up. This is a shorter one.
The Loess Plateau is an enormous region in northern China. Home to 50 million people, its valleys supported the growth of early Chinese civilization. The plateau is near the Gobi Desert and is naturally dry. With little water available, plants grow slowly and soil is thin. In ancient times, farmers cut down forests for wood and fuel. Without roots to hold soil on steep slopes, it began eroding. Livestock ate any trees that resprouted, and root networks were broken up by plowing. Soil kept eroding downhill, taking nutrients with it. During rains, plants and soil couldn't absorb water. It poured off slopes, carrying soil down to the Yellow River. This gave it its color and made it shallow, leading to more frequent and intense flooding, even 1,000 miles away. Over centuries, this transformed a once lush region into degraded, barren desert. People found ways to farm, but could no longer produce as much as they used to. With less food, there was more poverty and hunger. Today, without moist soil to store rain, the dry, sandy soil blows away in dust storms, into cities, and even out of China. In the 1990s, Chinese agricultural experts and planners developed methods to restore the plateau to its former productivity naturally by planting trees. At first, it was hard to convince everyone that this was a good idea. Many of the trees didn't make food and grew in farmland. Finally, when they realized they would benefit together, everyone agreed. They all worked together to transform the slopes. Trees were planted on hilltops to hold the soil in place. They kept their livestock away, since they would otherwise eat the growing trees. Farmers fed them leaves and branches from the trees, and they got payments to make up for lost crops. Right away, the effects were dramatic. Along slopes, terraces caught rainwater, which seeped into the soil. Instead of flowing away in a day, it stayed in the ground to feed plants over months. Crops, herbs, and bushes grew on the slope, holding them up, and made year-round harvests. The abundance of fruits, vegetables, and animal products tripled the income for villagers, and provided enough food and medicine for all. Flooding has been reduced in the Yellow River, and dust storms are less intense. What's more, enormous amounts of carbon dioxide were captured by the trees, and especially the rich soil, helping to fight climate change. With a quarter of the world's land in similar degraded states, planting trees may make a world of difference.
Okay, there we go. All right, we're gonna start the lab. So I have some water boiling over here, and I'm gonna bring this right over here because I have a plug. I'm gonna plug it in here, but I'm gonna add something to the water. And what I'm gonna add to the water is salt. Okay, so y'all are gonna end up drawing this whole apparatus that we put together here. It's called the distillation apparatus, the poor man's version.